Welcome to Cadence Legato Memory Solution webinar. I'm Joy Han, and I'm on the product management team at Cadence, responsible for Spectre circuit simulations and Legato Memory Solution. So first, why we decided to work on Legato Memory Solution? Why we decided to work on Legato? Why the name? Second, why memory solution? First, Legato name. The name Legato is actually a musical term. Very much like a Cadence, our company name is a musical term as well. Legato means that each note when you're playing, you have to connect them smoothly. And this is very much of an illustration of what we're doing in our memory solution. What we're doing is we're creating design, verification, and characterization all together and seamlessly integrated all together. So that's why the name Legato. And why we're addressing memory, the reason being is memory is, if you look at it, it occupies the most real estate on the die. If you look at our research, it's showing that it's going to even occupy more space. So if we could address the biggest real estates on the die area, and we could certainly help designers to meet the challenges. Secondly, because as we move down to advanced node, the number of PVT corners that is required to accurately capture the design has increased significantly. So with us moving to advanced node, we're seeing that we are reaching close to 200 PVT corners, and all this means there's a lot of simulation, simulation time, and so it's certainly a big challenge. And the third, if you look at Moore's law, and basically says that in 18 months, and the number of transistors on is going to double. And what we have seen is that with Moore's law, it requires quite a bit productivity improvement to catch up with what's happening in the silicon industry. And what we wanted to see is that the productivity that we could catching up with what Moore's law is requiring. So with all these challenges, what we have decided to do is to introduce this Legato memory solution. So I talked about the Legato, the meaning of Legato, and now you look at it. What Legato memory solution consists of is really 3 cockpit. We have the design cockpit, we have the verification cockpit, and then we have the characterization cockpit. In the design cockpit, what you do is you use silicon-proof SPICE simulators, and you run Monte Carlo analysis to get the yield estimation. And then once you're happy with the design, usually in the design phase, you use it for bit cells or sense-amp. And once you're satisfied with that, what you do is you move to the verification cockpit. And in the verification cockpit, what you do is you verify the entire memory array, and you make sure the timing and the power is all meeting your design specification. So after you verifying and you making sure it is accurately meeting your spec, then what you would like to do, most likely, is you need to create a .lib format of that memory array that you have just verified. And then the reason you want to create the .lib format is that you want to take the .lib and to do the rest, with the rest of the design, to do full chip SoC. That .lib has to accurately reflect timing, noise, power, leakage, all that information. It needs to accurately capturing what is your memory array is doing, so that you could making sure when you do the full chip SoC, it is working as what you would like. So if in the design cockpit, what you would require is an accurate SPICE simulator. And here, we have the Spectre circuit simulation. it would definitely meet the need. Our Spectre simulations are silicon-proven, golden spice simulators. And you also need effective failure rate prediction. If you look at each unit circuit, the failure rate is actually quite small. But what happens here is a real failure rate of a unit circuit can introduce actually a pretty significant failure rate for the entire system. So what I have here is I used 1 megabyte of SRAM as an example. Even though each unit failure rate is quite small, the failure rate for the entire SRAM system is actually quite significant. So that's why, in the design, what we are trying to provide is we're trying to provide you the accuracy, and we're trying to provide you the failure rate prediction. And in the design cockpit, what customer would ask for is they want to have a very accurate spice simulator. And usually, even at an advanced node, the criteria is quite stringent. So you're talking about 2 picoseconds or 2% for timing, 5% for dynamic power, and 20% for peak. So the criteria is pretty strict. And so we want to make sure that we have an accurate spice simulator that can meet those criteria. What we're doing in the Legato Memory Solution is we also included a patent-pending super sweep technology, which I'll explain later on. With that patent-pending super sweep technology, it helps you to maximize your simulation throughput. Because here, you actually simulate the entire memory array. You want to make sure that you get the accuracy and also at a reasonable simulation speed. So with the super sweep technology, it enables you to do that. And the last, with Spectre XPS, the Spectre circuit simulators, we have the ability to consider full VPN effects. And as we move down to the nanometer design, considering the VPN VPN effects is a must in order for you to meet the accuracy criteria that I mentioned early on. So here is an example of the VPN effects that I'm talking about. This is a sub 10 nanometer SRAM. And what we are doing here is we're looking at the read cycle time, RCT. And you see two lines, one is red, one is yellow. The red one is considering the VPN effects, and the yellow one does not consider the VPN effect. As you can see, if you do not consider the VPN effect, the RCT signal is 28 picoseconds early. And this is as I said, this is a sub 10 nanometer SRAM with 256 K memory cells, and as you get the memory size gets larger, the error is actually going to get larger as well. So as you can see, to be able to really effectively taking the full VPN effect into consideration when you do verification is really a must in order to meet the criteria we talked about early on. So what we have done here is that with the Spectre XPS technology, which integrates with the Legato Memory Solution, and what we have seen is that when we do in the SRAM, for example, in the memory, what we have noticed is that the memory is not going to be active. All parts of the memory is not going to be active at the same time. So what we have seen is that you may see some activities on the bit line and word line, and then the rest of the area is pretty quiet. So what we're doing here is that we are applying the single rate based solver for the part that is active. So we're making sure that the active region are getting the really good accurate single rate solver, and we're also making sure that they get conservative RC reduction conservative step control. So that way, we're making sure that you're getting the accuracy you needed for the active word lines and bit line. And for the region that is quiet, we can provide basically more large step controls on these non-active area. We could apply aggressive RC reductions in the non-active area. So that way, we can making sure that you are getting the accuracy, but at a much better performance. That's a unique technology in our simulator. And I talked about the patent pending super sweep technology. And so here's an illustration of that. Without the super sweep technology, what we have seen today is with each PVT corner simulations, it's independent. So basically, if you're going through 200 PVT corners, what that means is you're going through 200 independent simulation. So each simulation would go through simulation front end, RC reduction, partition, table model generation, DC, and the transient. So with the super sweep technology, what we're doing is we're looking at it and to see if there's any simulation data that's available that we could utilize. So what our research have shown is that, for example, if I'm just changing the input slew and output loading, I'll be able to leverage the simulation data after DC, before transient. So that way, I could really increase my simulation throughput. This is a time when people ask me, with the super sweep technology, what kind of speed up you're going to see? The answer is it really depends on the design, because it depends on if the transient time as a total simulation time, what's the percentage of that? If the transient time comparing to the total simulation time is small, then what you will see is a very significant simulation performance improvement. If the transient simulation time as a percentage of the total simulation is large, so in other words, all the previous step, simulation front end, RC reduction, partition, table model generation, DC, these are relatively quick, and the transient analysis takes the majority of the simulation time. In those cases, you may not see a significant simulation throughput, because what we're doing is we still need to do the different transient for each simulation. So this technology, the super sweep technology, we utilized it for the multi-corner PVT. Also for Monte Carlo analysis, we're utilizing the same technology as well. So in the characterization, we have Cadence has a Liberate MX solution, which is really a unique memory solution on the marketplace that helps you to create the library characterization models for the memory. And what we're doing is that, with the Liberate MX, it leverage, you could use the distributed CPUs, and you could use the unique technologies within Liberate MX to optimize your characterization runtime. And now what we're doing is we are taking the Liberate MX product, and it's a part of the Legato Memory Solution. And what we're doing is we enhance the integration between Liberate MX and our simulator. And just a note, Liberate MX continues to be a standalone product. So if you're a Liberate MX customer, and you do not need Legato Memory Solution right away, you could continue to use Liberate MX as you have been. So here is an illustration of the Liberate MX technology. So what we take the tickle, we take the spice netlist, and we take the stimulus, and all goes to the Liberate MX. And what the Liberate MX does is that it automatically identified the probes on the sensitive nets, so that we're using a dynamic static analysis, so that we're making sure the sensitive part of the circuits are getting the attention, so to ensure that you're getting the accuracy. We also have the dynamic partitioning technology. And what that means is that, with memory, and it gets really large, and what we do is we are identifying the critical path, and with each critical path that we identify, we have the capability of carve out that critical path with all the branch information actually captured. So that way, for the critical path information, what we can do is we could carve out, we use the dynamic partitioning to carve out the netlist for each critical path, and so that you could use a more accurate SPICE analysis simulator to run on that netlist. So what that enables you to do is it enables you to get accuracy, because now, instead of simulating the entire memory array, all you have to do is you are simulating this critical path with all the necessary branch side effects captured, and so that you could use accurate SPICE simulator to analyze it. And we are using, it's fully integrated with Spectre XPS, so that when we do is we could read in the design, we could use partitioning technology to partition the design into small pieces. And with each small pieces, you could use either Spectre APS or Spectre XPS to complete the simulations at the leaf cell level. Okay. So in terms of who are we targeting? We're targeting, for example, the memory IP vendors, and these are the foundries or memory compiler companies that they provide memory as IP, and these are obviously the target customer for us. We also have SoC designers, and these are the people who design memory on their own, or they use memory compilers. They do customization on top of that, and these are certainly people can benefit from our Legato Memory Solution. And we also have some standalone memory chip vendors, and where their entire the chip is just act as a memory, and we have such companies, and that would be a good target customer as well. So in terms of the benefits, is that now I talked about the design challenges at the beginning that's facing the memory designers and verification engineers. And, this is all in a climate of faster time to market. We have very aggressive design schedule. We need to deliver the design accurately with the first silicon success, and so the productivity, that requirement is very significant. What we're doing here is we're providing design, verification, and characterization all together as a one-stop shop, and so that you could navigate in a different design phase, and still while making sure that every pieces works smoothly. What we do is we have shared engines across design, verification, and characterization to make sure you get the consistency of the results, so that you're not going to be spending time to debugging your tools or your flows, and instead you could focus on your design. And we also have enhanced better integration between the cockpit and the simulator, so that to make sure that you have the best throughput, the best integration between the Legato Memory Solution and the circuit simulation. So in that we have with Spectre circuit simulators, we have what we call the common simulation front end. And what that means is that, with all our circuit Spectre simulators, such as Spectre or Spectre APS, Spectre XPS, we have this common simulation front end. We have the same device model support. We have the same netlist parser to ensure that if you move from APS, Spectre APS to XPS, you are getting the consistent accuracy. We have also enhanced the integration between the Liberate MX characterization and XPS. And what we're doing is we have improved XPS accuracy for advanced node. And I talked about the accuracy improvements that we did, where we use topology recognition. We identify the active bit lines and word lines so that we could use the single rate solvers. So that way we're making sure you maintain the accuracy and improve the performance at the same time. And what we have also done is with the XPS and Liberate MX integration, we have the partitioning technology, and then once it gets partitioned at the leaf cell level, you could use Spectre XPS or APS, any Spectre simulator to simulate and to get the accuracy results. Okay. So now I am going to talk about some demos that we have shown. And the first demo I'm going to show you is the super sweep technology used for multiple PVT corners. And here is we will demonstrate to you the patent pending super sweep technology. How does that work? And here is the example is we need to create a 7x7 input slew output load table. And we also changed a 3 variation on voltage. So the demo actually illustrates 3 runs. We run the Spectre APS. That's our accuracy baseline. And so we want to make sure that if we run XPS without super sweep or with super sweep, we will see similar accuracy as we get from Spectre APS. And then we will run 2 Spectre XPS runs. One is using Spectre XPS with super sweep, one is without, and that's when you will see what kind of performance improvements that we get. So here is the demo.
So here is the demo outline for super sweep technology. In this demo, we will show accuracy correlation with Spectre APS and runtime comparison with and without super sweep technology. We'll choose a sizable design for this demo and we'll do the following 3 runs. The first run would be run with Spectre APS to establish accuracy reference. The second run would be with Spectre XPS in the memory solution with the super sweep technology. The third run would be with Spectre XPS without super sweep technology. Let's look at the setup. We'll start with the input files. So here we have 3 directories: APS, XPS with super sweep, XPS without super sweep. Let's go to APS input file. So we are using the same netlist for all the 3 runs, and here we can see we have this C load, slew and VDD variation. So we have 7x7 slew load table with 3 voltage variations amounting to 147 simulations. These are all the alters. The command for running APS would be Spectre with APS engine. Let's look at the XPS without super sweep file. So here we are invoking the Spectre plus XPS. Now let's go to XPS with super sweep. Here the run command has the same XPS, Spectre XPS, with the following CFG. Let's open this. So it has the dot option super sweep equal to 1 to invoke super sweep feature inside XPS. Let's start the demo. So it has started running. Once it finishes, we can go to the output directory. So let's look at the accuracy first. So we have these two measurement files which we can open with the tkdiff and look at the accuracy. So we have very good accuracy in both absolute values and relative values. It has all the 147 values for this measurement. Let's go slowly. So these are the all 147 simulations. If you look at here also, it has still very good accuracy. We can also look at the accuracy from waveforms. So this is the same measurement which is measuring from pre falling 50% to D out 0 falling 50%. The yellow is APS signal and the green is with super sweep, and we can see a very good overlapping in the correlation with the two signals. So now let's go to the performance comparison. So we have our log files for without super sweep and with super sweep, total CPU time. So if we look at the time in seconds, we can see that with super sweep is 2.3x faster than without super sweep.
So also the second part of the demo I would like to show you is LDBX in the Liberate MX solution, which is now which is also a part of a Legato Memory Solution. And so the Liberate LDBX stands for Liberate Database Explorer, and it's the previous name, formal name was DMS, and now that we're moving forward, the product is called the Liberate Database Explorer. And what that enables us to do is we created a Python interface to the library database, and then what you can do is you can operate on it operates on the library database or .lib, and it's available, as I said, the Liberate MX available as a standalone as well as a part of the Legato Memory Solution. So this feature is available in both. The benefits of this feature is that it allows you to improve productivity by enabling you to do query, modification, and copying or visualizing of your library database. I included a Python script, and this is a Python script that we actually run in the demo as well. So here what it does is that it gives you the ability to look at the LDB, and so you could get LDB, so you could load the design database, you could get it, and you could print it, and you could plot it. You have the mplot where it enables you to plot, and then you could also here it allows you to add margin into it. There is the m.lut line here, and it enables you to add margin in conditional add margin. And so that what it enables you to do is that you'll be able to modify the library database as well. And after you do everything, you could do the mplot, and which enables you to visualize the library database. So now, with this, I'm going to move and illustrate the demo. And in the demo, you will see a copy of this Python script and also how it helps you to do the query, do the modifications, and as well as to the visualization of the database.
This part of the demo, I'm going to show you an example of how the data manipulation system can be used to access the full library, how to access a specific entry and lookup table in the library, how to modify it, and finally how to display the result graphically before and after the modification. All these operations are contained into a Python script, and that can be run through Liberate MX through this simple command. To give you an idea of what this script contains, this is very basic set of containing very basic set of commands to load the library, find a match for the specific arc we are interested in, and then print some information about what was obtained, the specific lookup tables contain, and how to access that information. Add a conditional margin in the sense that we're going to add a very large number so that it's going to be visible in the final graph to one point in the table, one or more points on the table that satisfy a specific condition. And finally, we're going to plot the results before and after. Simple command to load the Python script from inside the memory cockpit. And what you see on the screen following this command is simply a trace of all the different commands that we described. So here we're showing the first plot of the lookup tables, delay values for the delay arc that we matched and obtained from the library. In the axis, you see the slews, input slews, and output loads, and this is the behavior that you would like to see, obviously, in a characterized data, where monotonically values are monotonically increasing with slews and load. After we do the modification of adding a very large number to those entries that satisfy a specific condition, and redisplay that data, you'll see, obviously, that change showing up as a big discontinuity in the curve. That concludes my presentation. Thank you for your attention.
So we have introduced this Legato Memory Solution and in September of this year. And Socionext is one of our early customers, and they have used our Legato Memory Solution. They have experienced about 2x productivity gains when comparing with their point solution, and they were able to use it, Legato Memory Solution, to tape out 12 nanometer memory macro designs for their SoC solutions. And once they get the silicon back, they were able to confirm good correlations between the simulation results and the silicon measurements. So this is the experience that we have seen from Socionext. Invecas in India, Invecas is a global company, but at the CDN Live India, they have presented a paper on their experience using Legato Memory Solution in the context of AOCV. And what they did was they look at different methods that they have, to run the full instance, or to do some critical path simulations, or to use the Legato Memory Solution. And they comparing the runtime and runtime memory. And what they have seen is that use the Legato Memory Solution, they see exponential savings in runtime and run memory. So we also have their experience captured in the video, and you could see that on our homepage, Cadence.com homepage as well. So if you'd like to get more information you could go to www.cadence.com/go/Legato Memory, and you will see other videos that we have. You will see our overview video that's given by Vinod, our VP of R&D. And you will see different cockpit demos that's available as well. Thank you very much for attending our Cadence Legato Memory Solution webinar. And if you have any questions, feel free to submit the question or contact your Cadence sales rep for more information. Thank you.